What is inductively coupled plasma atomic emission spectroscopy? ICP-AES is a quantitative chemical analysis technique used to determine the amount of certain elements in a sample with high precision and accuracy. Before diving into the science behind this analytical technique, let's look at the common states of matter which we can observe in nature. Water, for instance, is commonly found in its solid, liquid, and gas phases in nature. But there's one state of matter which is often forgotten: plasma. Certain gaseous substances turn into plasma if they're heated sufficiently. In the plasma state, electrons are stripped off atoms and move freely amongst cations. In our day-to-day life, we see plasma in flames, lightning, and the sun. But how does this link to ICP-AES? Many scientific inventions that change the world have been inspired by nature. The principle of the ICP-AES relies on argon gas being heated until it reaches the plasma state. The energy is supplied by electric currents, which are produced by electromagnetic induction, hence the ICP part of the name. When atoms are heated, the electrons absorb energy and get promoted to higher energy levels. In the ICP technique, the source of the heat is the argon plasma, which has a temperature of around 10,000 Kelvin. When electrons return to their ground state or to a lower energy level, they emit a photon of light with a specific wavelength. This wavelength depends on the energy gap between the orbits which the electron transition takes place. For a single element, there could be multiple wavelengths of light emitted. This is due to multiple electron transitions which can take place from a higher energy level to a lower one. The diagram shows the energy gap between the two energy levels for one possible electron transition. The same electron could be promoted to energy level 3 and return back to energy level 1, which is called as ground state. The energy gap will now be greater, so the wavelength of light emitted will be slightly different. If we know delta E as shown on the diagram, we can use the equation E equals hc over lambda, where E represents the energy of a photon, h is Planck's constant, c is the speed of light, and lambda is the wavelength of light emitted. The gaps between energy levels are unique to an element, therefore different wavelengths of light will be emitted by different elements. The ICP-AES measures the intensity of light emitted by the sample at each wavelength to calculate highly accurate concentrations of the element in the sample. Before carrying out a sample, the ICP-AES machine is calibrated using solutions of known concentrations. This creates a calibration graph which shows the relationship between the intensity of light emitted at specific wavelengths and the concentration of the element in the solution. This graph is then used to determine the amount of the element present in the sample itself. The ICP-AES has many uses in a variety of industries. It is widely used in food quality control and mineral processing due to its ability to detect concentrations of elements even if they are as low as a few parts per million.